form of conjunction. Now, the first three statements together give rise to a language that's equivalent to SUDSI, simple distributed security infrastructure, a language that was proposed in, I think it's 1996, and later sort of combined with spooky, simple public key infrastructure. But I mention this because a fair amount of work has been done on how to provide a semantics for SUDSI. We'll actually take a different approach to providing the semantics for RT, and I'll, in my next slide, give you some explanation as to why that is. But in this slide, I'll briefly show you the construction of that semantics. It's based on constructing a logic program, in fact, a restricted logic program called a data log program. And the way that it works is that for each statement in the policy, you get one clause in the data log program. So the first form of statement, A.R includes D, gets translated into the simplest form of clause often called a fact, in which M is the membership predicate. And this just says that D is included in A.R. The second form, in which A.R includes B.R1, is translated into something that just uses the membership predicate to say almost exactly the same thing. So this little symbol right here is read if, and this says that X is in A.R if X is in B.R1. That captures the intuition that I think you'll agree is natural. In the third form, we want to say that, well, it's just translated into X is in A.R if there exists a Y in A.R1 such that X is in Y.R2. And finally, intersection just turns into conjunction. So now the semantics is defined in terms of logical entailment. So if you have D, a member of A.R in all models of the program, then the semantics says that D is in the role A.R. So one of the neat things about using logic programming to construct the semantics is that it makes the complexity results really easy. Data log has been studied a great deal, and it can be evaluated in a time that's a small polynomial. Other semantic foundations don't support features that we really want, like, for instance, even intersection. So the string rewriting and pushdown systems are approaches that have been used for providing or evaluation of SUDSI, and neither one of them is really suitable in a context where you've got intersection. Moreover, using the logic programming approach enables one to easily extend the language to incorporate those extra features like parameters, thresholds, and separation of duty. So at this point, I'd like to switch gears from talking about the basic language and tell you a little bit about security analysis. So the goal here is the understanding and management of these distributed authorization policies. The reason is that authors of policy statements need assistance in understanding the global impact of statements that they add or revoke. Indeed, others may also need assistance in understanding the situation with a policy. They need to understand who could get access to what and who could be denied based on the fact that the policy may actually evolve in a situation where not all, no given entity controls the entire policy, and hence it is going to evolve beyond the control of any one entity. So I'm particularly proud about this work, in part because it's going to be published in the Journal of the ACM. And again, my co-authors are Ninghui Li and John Mitchell. In this part of the talk, I'll give you some background on the security analysis problem. I'll describe the abstract case of security analysis for trust management, and then make it concrete for the language RT. Then I'll discuss a couple of usage scenarios and the complexity results that we obtained. So, security analysis actually has a long history of study. Going back 30 years, a subproblem called safety analysis has been studied, and in that work, the access control model was based on an access control matrix. So the idea with an access control matrix is that rows correspond to subjects, columns correspond to objects, and the cells give you the access rights that that the subject has with respect to that object. Now, this forms the state of a state machine whose transitions correspond to the execution of commands of the form shown here. A command tests to see whether several rights are in given access cells, and then, if so, executes a sequence of operations that can enter new rights into cells, remove rights from cells, add or delete columns or rows. And now, in this model, a system such as this is deemed to be safe if there's no sequence of commands that gives a given right A to a particular subject S on object O, where A, S, and O are all given. And Harrison, Rousseau, and Ullman showed in 1976 that determining whether a system such as this is safe is actually an undecidable problem. So there was subsequently a fair amount of work trying to figure out alternative systems that would give decidability. And it's very interesting, I think, that in the trust management context, what we found is that the analogous problem is not only decidable, but it's decidable in polynomial time. So let's take a look at what the analogous problem is in trust management systems. Basically, evolution of the system, or transitions, now corresponds to the fact that an individual doesn't control the entire policy state, and other parts of the policy state can be changed beyond his control, or in an uncontrolled way. And to capture this notion of uncontrolled changes, we introduce the idea of a restriction rule R, which says how a policy state P can evolve into another policy state P prime. And given this framework, we can articulate two different forms of analysis problem. An existential analysis problem asks whether there exists a P prime reachable from P in which certain query holds from P prime. And a universal analysis problem asks whether in all policy states reachable from P, the query holds. So let me give you a few examples of the kinds of things that you can phrase this way. Can Alice ever get access to the database? This is a simple safety question because basically you don't want Alice to have access and you're worried about it. Will Bob always have access to the database? Now, presumably, Bob is somebody that needs to have access, you want them to have access, and you're worried about the resources availability to Bob. We can also articulate other things like bounded safety. Can anyone besides you and me ever get access? Or liveness.